Okay, this notion is sufficient. The number of items or the number of bits, as the case may be. Again, the number of items that we are going to take may be expressed in terms of single parameter or multiple parameters. Okay. So, the number of items may be, the variation in the number of items can be expressed through single parameter or multiple parameter. I will give example of both. Sorting, for example, can be very easily expressed through single parameter. Okay. The number of items you are taking into process, you may denote that by n, which is a very common practice. N is the input size, which is the number of values you have taken for sorting. Okay. But if you are using graph, for example, a graph may have n vertices and m edges. So, multiple parameter, for example, a graph, okay, it may have n vertices and m edges. If you are multiplying non-square matrices, for example, here you have a P by Q matrix and you have a Q by R matrix. When you multiply this, what is the labor involved? What is the total number of multiplication? The total number of multiplication is PQR. So, the complexity, the number of operations is now expressed in terms of 3 parameters. Here P can vary, Q can vary and R can vary independently, and using this formula you can find out what is the labor in multiplying a 10 by 10 with 10 by 1000 matrix or 7 by 13 with 13 by 42 matrix. Right? P, Q, R could be independent parameters. If there are square matrices, you can take, for example, one parameter itself, namely the dimension itself can be taken as the input size. All we need is a quantity which is reflecting on the quantum of input that we have taken, and the variation in that quantity should reflect on the variation in the quantum of input we process. So, for sorting, the number of inputs is a perfect and ideal one. It is a single parametric one. For others, you may need multiple one, or you may ignore some of them and take the largest one, and so on. You can do variety of mathematical simplification, but what is important is the input size is always given through one or more parameters whose variation will capture the variation in the quantum of input we process. Okay? So, it has to be chosen meaningfully. It has to be chosen in such a clean way that my variation is indeed giving the right amount of variation in the quantity and it correctly captures the time complexity. So, after getting into the input size, he made the following observation, the third common sense observation: larger the input size, more will be the instruction, right. Therefore, there is a functional relation between the input size and the instruction count. Third, what he said is there is a relation between input size and instruction count. There is some relation, and this relation is called time complexity function. So, after introducing the notion of input size and debating on various pros and cons, we go to the next stage of time complexity function. Time complexity function. What is this function? Function means it has to relate two things. What does it relate? It relates the input size to the instruction count. Why should it relate? Because when the input size is increased, the labor you perform also increases. So, how are they related? That is what we are interested in looking at. So, time complexity is the complexity function is the next concept that but there was one minor hitch here he encountered. You have to relate the input size to the labor, but even for the same input size, different inputs may have different amount of labor. To appeal to your intuition, let us consider sorting again. You take sorting of 100 items. Sorting 100 items which are thoroughly scrambled may call for a lot of labor and data movement than sorting 100 items which are nearly sorted and only minor tinkering is needed to set it right. Okay? That means you may take 100 numbers to sort, but there are several sequence of 100 numbers are available. Each one may call for different amount of labor. If that is the case, which labor would you take it for associating for time complexity function? Okay? This is where he came up with a brilliant suggestion on the notion of worst case complexity. So, worst case complexity says of all the inputs of given size, for each input of given size there is a corresponding labor involved. Take the maximum and that number you associate with that size. Okay? So, to simplify our discussion, let us take the input size being described through a single parameter, say n. So, you take input of size n. There may be several inputs of size n. For each input of size n, there could be different instruction counts. Take the maximum of it, and that is going to be the worst case complexity. So, how do we symbolically denote it? We do this using the following. Suppose for an input I, the corresponding instruction count is denoted by IC of I. We will also denote by IN the set of all inputs of size n. Now, worst case complexity of n is defined as maximum over I belonging to IN of IC I. That is all. Formal mathematical definition is given here. You consider the instruction count I as the individual one and you take the maximum. Okay? So, consider all the inputs of size n. For each one you find out how much it, take the maximum, and that is the worst case complexity. And this function of n is what we are interested in. Okay? And this is called the time complexity function, or what is known as worst case complexity function. Worst case complexity function. So, worst case complexity function is formally and mathematically defined like this using these two simple notation. No big magic here. You can extend this for multi-parameter. That is a trivial straightforward exercise. Overall inputs of size A, B, C, take the maximum and parameterize through those three variables, you get it. Okay? So, this is how the worst case complexity is defined. And he took two further steps and completed the list of all principles. What are the two further steps that he has taken to complete the entire discussion and setting the foundation? Let us take a look at them now. The first one is, I said instruction count. Which instruction? If you take matrix multiplication, that process involves addition, multiplication. Which one you should choose for measuring the time complexity? Okay. So, this is where he suggests the following. Take the dominant operation, that is because there should be, your time complexity measure should have some bearing to the running time. So the dominant operation and their frequency will give you the rough indication on the running time. It is not an exact indicator, but a rough indicator. Why he is trying to simplify this? Many problems are not as simple as matrix multiplication problem consisting of only two simple operations. Getting the instruction count for all instructions involved in that process is mathematically tedious job. And after doing all of that, you are not getting any more insight than what you would have otherwise done with the dominant operations. In practice, when he felt all these things, he suggested the following, okay? Micro analysis and macro analysis of the algorithm. Micro, macro is a terminology which is commonly used to describe two levels. Micro means in all complete details. Macro means at a very high level. So macro analysis of algorithm consists of computing the instruction count for only few selected operations. Micro analysis, on the other hand, involves the performance of or finding the instruction count of every instruction involved in the process. Knuth has written 3 volumes. In his 3 volumes, he has done the micro analysis. Okay? He has taken every instruction for, he will write a program, he will explain the idea behind that, and then he will go about the analyzing it, take every instruction and show how much it counts to. Okay? Very thoroughly written book. Incidentally, Knuth's book has been declared as the book of the millennium. Right? It is not book of the century, book of the millennium. There are only few books. There are 10 books people have identified as the books which are written with a distinct level of class and authority. Knuth book gets into one of them. Another one is Dirac's book on science. It's the greatest volume. There are certain great volumes and great ideas explained in certain way which are unbelievable, unbelievable. Knuth's book is a class by itself. Okay, so there are people who say we should have 2 copies of Knuth, one at office and one at home, and people who say there are 3 copies, one at office and one at home and one in your car. Okay, that is, you should never be away from Knuth's book from an arm's distance. Always you will need it. It is such an encyclopedia and wealth of ideas in that, and that's why it is a celebrated volume. Anyway, so what we have is macro analysis, micro analysis. Micro means all instruction. Macro means selected instruction. Obviously, you have to be very wise in selecting the instruction. If you are careless in selecting the instructions, the conclusion you get may not bear anything with the reality. Okay? Micro analysis and macro analysis. And one final thing with which he has completed it, and we will also be completing our first half of the session. Okay? By 3:30, I promised them that I would give the break, and we will hit the clock after discussion on the second and final part of the principle. Another common sense criteria that he has observed is the following. We are using computers as a tool to solve larger and larger instances. In other words, we are interested in the behavior of the problem, or the notion of efficiency becomes relevant only when we consider a very large sized input. Okay? Whatever is the algorithm for sorting, if you are sorting 10 items, it really doesn't matter which algorithm you choose to really implement. The instruction count may vary marginally for 10 inputs. One may take 12, another may take 11, another may take 15, but everything will be over in less than a fraction of a millisecond. But when the input is very large, 1 million records, okay, one may take 1 million into 1 million, okay, so 10 power 10 operations. Another one may take hardly 16 or 15 into 1 million. In other words, more than 10,000 to 25,000 times faster than the other algorithm. Okay? So this will be revealed only when you study the properties of the algorithm as the input becomes larger and larger. In other words, what we are interested in is not only just that function, but we are interested in the growth rate of that function. How it becomes larger and larger as the parametric value or the input becomes larger and larger. Okay? So, suppose you take 500 n and 1 by 10 n square. Suppose this is the complexity of algorithm A1 and this is the complexity of algorithm A2, the function, hypothetically, let us assume this. If you take n equal to 10, this becomes 500, 5000 for n equal to 10, and this becomes only 10. Okay? So looks like this is far more better than the other one, but it is not actually the case. As n becomes larger and larger, because it has got higher growth rate, this will become much larger eventually, and then this will become nastily larger than this, that there is a point beyond which this will become much smaller than this. In fact, in this simple example, we can see that 5000 is the threshold. At 5000, you see both the curve will meet. Beyond that, the n square curve will go very steep, the n curve will go slant. In other words, beyond 5000, if you look at the value, let us take 10,000. If you take 10,000, 500 into 10,000, if you look at 10,000, okay, 500 into 10,000 will be 5 into followed by 2 followed by 4 zeros. But this one will be this is 10,000 and this is another 10,000. You have to divide by 10. So 1 0 goes off. You can see that this is the value. Quite a bit higher. In fact, as n becomes larger and larger, this is going to become larger than this forever. Why? Why this happens? That is because the growth rate of this function is higher than the growth rate of this function. As n becomes larger and larger, this also becomes larger, this also becomes larger. But the rate at which this grows is far more than the rate at which this increases or this grows. That is the reason why beyond some point you see that this not only catches this value and this overshoots that. Pictorially, you can see that this n square curve is going to be something like this, this n curve is going to be something like this. So up to this point, all these values might be smaller. For example, the n square, 1 by 10 n square is smaller, this is very large. But up to after some point, let us say after 5000, this will become smaller, whereas this will become unimaginably large. Okay? So what he discovered is when people are all fighting for their efficiency by running an input, all these people were running on an input of size 10, 12, 15 and saying that this is taking 1.2 millisecond, that is taking 1.3 millisecond, therefore this is faster than that. That was actually meaningless. Maybe with a little bit of a clever programming, one can be made to work other. The idea may be good, but the implementation could be bad. So you will never be able to see all these kind of variation for smaller inputs. Therefore, what is important in practice as well as in real life is the behavior of the algorithm when the input size becomes larger and larger. Okay? Study of any function as the parametric value tending to infinity is called in mathematics as asymptotic analysis. So asymptoticity means studying the behavior of the function as n becomes larger and larger. In other words, as n tends to infinity, how this behaves and how this behaves, and what is their relative behavior. From this, can I make an assessment on this is going to be better eventually than this. Hence, for sufficiently large input, I would like to, though initially this appears to be a very inefficient one, eventually this outperforms this one, so I would like to choose this with my future in my mind. Okay? Long 30 years back, the number of students who would have written the school final exams would be hardly less than 1,000, but now it runs into lakhs and lakhs, and in future it is going to become crores and crores. So many problems are like this, they will become larger and larger and larger. So I must choose an algorithm that just not works for my current scenario, but I must choose something in which its a potential future, time proofing, that is achieved only by studying the properties asymptotically. Of course, there is a caveat here. Here the threshold point happens to be 5,000, but if the threshold is a very, very, very large number which you are never going to encounter, in that case, right, pragmatics dictates that you choose the n square one. Okay? Suppose this is 5 million or 5 trillion n, and this is 1 by, just for the sake of mathematical discussion. Suppose if this were like this, then the threshold will be something beyond 5 trillion or 10 trillion. Suppose in your application you are never going to reach that number. Yes, this algorithm is going to become eventually better than this, but the point at which this becomes better than this is beyond all my practical limit. In that case, pragmatics dictates that you choose this one. But then now you arrive at this conclusion after a scientific analysis. You look into the constant there, constant here, thresholds, compare the growth rates, where one beats the other. After looking into all of them, you choose one algorithm. It is not simple rush of a blood and running on 3 inputs, you conclude that one is better than the other. Okay? So this provides a scientific basis for us to compare the performance characteristics of 2 different algorithms, or many different algorithms, or many different ideas solving the same problem, and choosing the best one. In other words, effective use of the tool is enabled by this bunch of principles. Okay? We will next see how well this can all be put into practice. In other words, we have said growth rate is to be studied. How do you compare the growth rate? What are the mathematical tools available for it? And how the implication of this growth rate of an algorithm is to be interpreted in practice. All these things we need to clarify, and that is what my second session will address to. After that, about half an hour to 45 minutes I will be spending on that. Then, okay, you have 3 methods. All the methods are having complexity function whose growth rate is highly unacceptable. How do you find a new way of solving the problem? How do you come up with a new solution? Right? In other words, it is touching upon the third fundamental aspect of the human race, namely creativity. Okay? Something conceptually which was not even existing there, you conceive and create. Okay? Pyramids, so it was not natural, right? But somebody could imagine a big pile of stones and then build so many labors and whip them up and then construct it, and you can see the vision he had and the imagination he had. In fact, that is the reason why it is said every object is created twice, once within your mind, then the physical realization. Okay? So this creativity which is triggering that in your mind in some form is very important. Do we have some patterns for that creativity? How do we use those patterns wisely in arriving at efficient solutions for our problem? We will begin with one such pattern, which is called the paradigm in our parlance, and then get into the details of variations and subtleties and nuances of using that idea in our subsequent hours of discussion. So I will be able to, I will continue after the break on the big O notation, small o notation, omega notation, the mathematics for them, and cleaning up of the basics related to them, followed by a design principle and presenting before you a very simple, powerful and elegant design, and continue tomorrow with their myriads of variations and subtleties. Okay? This is what will be the agenda for the next few hours. Okay? To summarize, what we have seen was the following. The real life problems are to be converted into mathematical problem by a process of abstraction. Abstraction is a fundamental ability of the human race, and we use it to abstract the problem out. And we are always seekers of tools. Computers being a problem solving tool, we are trying to see how to use that. One way of using the tool effectively is arriving at efficient algorithm. And this begs for a question on what do you mean by an efficient algorithm? And if you want to capture the efficiency, we need to have certain principles which correctly positions the concept of efficiency. And Knuth has proposed the model in which several key features such as the notion of problems, time complexity, worst case complexity, input size, relating the input size to the instruction count, all of them were systematically studied. And then finally what was concluded is the growth rate of the worst case complexity function has everything to say about the quality of the algorithm. Therefore, we are going to study the growth rate of the complexity functions of the algorithms, and the process of finding that growth rate of the function is called analysis of the algorithm. So you are given a method, you study the instructions there, compute the instruction count, identify that function, and this process is called analysis. So the end result of analysis is that function, and once you have that function, that has got all the comment that it is supposed to say about the quality of the algorithm. This allows us to compare several ideas in a meaningful, scientific and rational manner. And with that, I stop my first session, and after the tea we will continue our discussions on the mathematical details as well as a paradigm. Thank you. Any questions? Okay, if you have no questions, we will adjourn for coffee and then meet here again. We had a brief look at the basic principles. Now we are continuing with our discussion on the growth rate. We have observed that growth rate is an important parameter to assess the merits as well as individual merit as well as the relative merits of algorithm. So how do we compare the growth rate? What are all the mathematical tools that are available to assess the growth rate? One of the basic notations that we need to assess the growth rate is big O notation. This is to be contrasted with a small o notation. That is the reason why we use big O and deliberately write like this. So big O of a function. I am considering at this juncture, for the sake of simplicity, function with only one parameter. This notion can be extended to function with multiple parameters. The discussion is simpler with one parametric function. Actually, rigorously speaking, big O of function f of n is a class of functions. So first I will give the class as defined formally, and then I will tell you how to meaningfully understand that class. This is the set of all functions G. Let us specify these functions. Let us introduce the notation. N is set of all integers 0, 1, 2, and R star is positive real numbers. Our F, G, these are all the functions from N to R star. What do you mean by a function N to R star? N, which we give here, is an integer. The reason is input size is generally going to be an integer, and hence we are not going to encounter fractions. So we assume that F, G, etc., they work on integer. In fact, the number of steps is also going to be integers. There is nothing like 3.7 steps. It will all be an integer, but still, for the sake of handling the functions which we are encountering, we are going to soon see functions like n log n, n log square n, and so on. In order to handle those type of functions, I have restricted that to a real number. So the value could be real, but obviously it should be positive. There just can't be a negative number. That is the reason why I am considering the functions from positive integers to positive real numbers. O of f of n from n to r star, such that this notation is for such that there exist constants c and n naught satisfying. So these are all the notation. There exist such that, or the common notation used. If this is puzzling, you write like that, like following. Such that there are constants c and n naught satisfying g of n is less than or equal to c times f of n for all n greater than or equal to n naught. This is the formal definition. Starts here and ends here. So there are constants c and n naught satisfying this condition. In fact, these are all positive constants because everything involved here is positive. You can qualify this as well. There are positive constants such that g of n is less than or equal to c times f of n. Such collection of function is called big O of f of n. If a function g of n is big O of f of n, we write as follows: g of n belongs to big O of f of n. So notice that big O of f of n is a set. So this function belongs to that set, and say g of n is big O of f of n. This is how it is read. G of n belongs to this set, and we say this as G of n is big O of f of n. Simple examples to clarify what this means. Okay. Let us consider f of n as 2n square plus 7n plus 9. Now I claim the following: G of n, which is equal to 20n square plus 6n plus 42 belongs to f of n. If I have to prove that it belongs to f of n, what is that I have to do? All I have to do is I have to find out constants satisfying this condition. In this particular case, I will show those constants. For example, the constant c equal to 10 and n0 equal to 1 works. Yes? You are right. Belongs to big O of f of n. This function belongs to big O of f of n. Yeah.
When you define the big O notation,
Yeah.
capital R, capital N and R star,
Yeah.
they are the values which small n can take.
Yes.
They are the range of values over which small n varies.
The small n varies, yes. F, yes, f is a function from n to r star means if you take f of n, n belongs to this set, n is an integer and f of n is positive real number. Okay. For example, if you take n equal f of n equal to n log n to the base 2. If n equal to 40, it is 40 log 40 to the base 2, which is a real number. Of course, if it is 8, 8 log 8 to the base 2, 8 into 3, 24, that is an integer, but for some numbers it is becoming real. So, in general, positive real numbers. Okay. For instance, in order to show that this function belongs to big O of f of n, I have to show you the existence of c and n naught. This works. How? You see that 20n square plus 6n plus 42 is less than or equal to 10 times 2n square plus 7n plus 9. It is obvious because right hand side is something like 20n square and 70n plus 90, and 20n square plus 6n plus 42 is less than or equal to 20n square plus 70 and 19 for all n greater than or equal to 1. In fact, even when n equal to 0, this is valid. Anyway, therefore, I can choose 1 as a threshold beyond which it is a constant multiple. Okay. So, I have proved that this is the case. Okay. I am going to show some more example unfolding the subtle points in this big O notation. Yeah.
So what the value of C we should take here? It should be 10, it should be 20, it should be 100.
C can be taken as 10. You have to show existence of one constant. So there can exist several constants. I have demonstrated one. Yeah, C equal to 100 also you can take.
First of all, that the threshold also will change.
Yes.
So what should be the minimum value of threshold here?
We are not bothered about those thresholds or the constant C. As long as you demonstrate that such constants and thresholds are there, we are happy. That's all.
Because based upon that we are comparing two curves.
No, for comparing two curves, we are going to have a different scenario altogether. This is only for the definition of big O. For comparing two curves, we will take exactly those expressions and then we are going to work on that.
So are we actually doing those algebraic systems and then comparing the two curves, or are we mathematically comparing two curves?
Depending on the level of information that we need, we have to work, right? In some instances, at a very high level, we will get the insight. In some cases, the high level analysis will not give, then you have to go to the lower level. So I will give the illustration of both the scenario when I continue with this example. Both your questions are going to be answered soon. Okay? So here I could have taken C equal to even 70. Even that would work. Obviously 20n square is less than or equal to 70 times this. That also works. Any C you can choose as long as you are able to demonstrate such a C. Okay, you say that this is big O of f of. Now I'm going to give you one function and you will see that you can never find a constant. Consider g of n equal to simply n cube. This doesn't belong to order of f of n. This is f of n. This is f of n. In other words, you will never be able to find a constant such that this is less than or equal to constant times f of n. N cube is less than or equal to constant times f of n. Such constant you will never be able to find out. Why you cannot find out? How to argue that you cannot find out? Well, this is where the following. Suppose if there is a constant, then n cube by f of n is less than or equal to C for all n greater than or equal to some threshold, whatever is the threshold. So n cube by f of n is less than or equal to C for n greater than or equal to some threshold. This is not possible if you consider n cube by 2n square plus 6n plus 9. This goes to infinity as n goes to infinity. So this ratio is going to become larger and larger and larger, arbitrarily larger. So beyond some point, the ratio cannot be bound by any constant. You say constant equal to 1 million, this ratio will exceed even that after some point. Okay? You say 2 billion, this ratio will exceed even that beyond some point. The reason is this goes to infinity as n goes to infinity. Because numerator is n cube, denominator is n square, you see that you cannot find such a C. Since you cannot find such a C, this doesn't belong to big O of f of n. Okay? Incidentally, this is the test we use for finding big O of f of n. Every time we are not going to discover this, play around with constants or do like this. We take the ratio of this, take the limit as n going to infinity and then see what happens. If that goes to infinity, then then g of n cannot be big O of n. In fact, its order of growth is more than the order of growth rate of f of n. Right? It is galloping to infinity at a faster rate than this. Both of them, as n goes to infinity, both of them go to infinity. But this gallops to infinity at a much faster rate than this. That is the reason why the gap widens and the ratio goes to infinity as n goes to infinity. Therefore, there is no way you can find such a relation. The ratio is going to become unbounded. Okay. All right. So, is n square is big O of this is n square belong to big O of f of n? Yes, trivial. The argument is trivial. Okay, you can find a constant. And what is important is, with respect to n square, it is working even the other way. Watch carefully this statement. I am going to argue that 7n square plus 8n plus 10 belongs to big O of n square. Is this true? You can do in two ways. One is you can find the constant. Another one is you can find the limit, and you can work either way. All right? So, first I will find a constant. When I find a constant, the way to find a constant is, I see that 7n square plus 8n plus 10 is less than or equal to 7n square plus 8n square plus 10n square, because this is less than or equal to this is less than or equal to this, which is equal to 25n square, and this is true for all n greater than or equal to, let us say, 5. In fact, n for all n greater than or equal to 1 also it holds good. I am simply writing like this. Therefore, the constant C equal to 25, n naught equal to 5 works to prove that 7n square plus 8n plus 10 belongs to O(n) square. In fact, this trick of adding the coefficients to find an ultimate constant can be extended, and we can say the following. Okay? Simply we can say the following: A0 plus A1n plus A2n square plus ak n power k belongs to order of n power k. What is a constant? Simply add all these numbers. If some of them are positive and if some of them are negative, take the absolute value and add them. Okay? If you have, for example, 7n square minus 10n minus 40, still you write it less than or equal to 7n square plus 10n square plus 40n square, for the sake of argument. Right. In other words, you take the absolute value. So, this clearly shows the following. If I have this, and I can write like this. Okay? So, what I have stated here is the following: 7n square plus 8n plus 10 is order of n square. In fact, is big O of how is the 7n square and n square, this expression and that is related? Over there, you are not seeing the lower order term, and you have ignored even the constant which is here, and you have got a very simple expression on the right hand side. So, ignore the lower order terms, ignore the constant multiplying the highest order term, you get a very simple expression, and that will give you the order. So how to show that g of n belongs to f of n? You take f of n, you want to show that g of n is less than or equal to c times f of n. In other words, g of n by g of n by f of n is less than or equal to a constant you have to show for all n greater than or equal to n naught. So study this ratio as n tends to infinity, and from this you can conclude. So as long as c is finite, you can say that Gn is big O of f of n, right? So Gn is big O of f of n if Gn by Fn, this divided by this, so 7n square plus 8n plus 10 by n square, it should go to some constant c dash as n goes to infinity. Is it happening? Yes, it is happening. In this case, okay, it is going to 7, which is a constant. So let me write down the first test of, okay, big O. G of n is big O of f of n if, so this is only a test, g of n by f of n goes to a constant, c is finite as n goes to infinity. That constant could be 0.
But we started with g of n is less than equal to c of fn. We have to divide both sides of an inequality by the same number, and the sign of the inequality has to be preserved, the number has to be positive, right?
Yeah, all are positive. Therefore, when you divide, huh? No, we are on the right hand side, we are not going to have 0. It's positive real number. So f values and g values are all positive values. But the limit can go to 0. I'll give an example. For instance, I can say 8n plus 10 also belongs to big O of n square. Perfectly possible, right? In fact, if you want to work with constant, 8n plus 10 is less than or equal to 18n square always for all n greater than or equal to 1. So 18 and 1 works for you, but I can use that test also. When I use that test, I have 8n plus 10 by n square. This goes to 0 as n goes to infinity. Yeah.
Example of n cube, right?
Yes.
And you say it is not a big O of this.
Yes, because it fails that test.
So we can't find any c or n naught.
You cannot.
What if you take 1 as c and n naught as 1?
Yeah, you cannot. See, it won't work. C and n naught equal to 1. N cube is less than or equal to n square for all n greater than or equal to 1. Is it true?
Not for all, because
It should be for all. For all values. So if you take the threshold as 1, it won't work. It's not true. What is important is for all n. That is the reason why as n goes to infinity, that will be discovered. If there is a violation, it will be tumbled upon as you make n larger and larger. Yeah, question there?
There will be a comment saying that C can be 0. As per the definition of big O notation, it is that C and Z0 should be positive constants.
No. According to the definition of big O, C could be 0. C should be only finite. We have another definition that is called the theta notation, and for the theta notation, C should not be 0. We will come to that next. The only difference between theta notation and big O notation is that C can be 0 in big O notation, whereas it cannot be 0, it must be finite and non-zero for theta notation. Okay? I will tell you what is the great significance of that, why it is very different. Right? It has some very subtle message to tell you. I will capture that soon. Okay? So, we have seen 3 examples. This belongs to ON square. This belongs to ON square, whereas n cube doesn't belong to ON square, and so is 5n power 4 plus 3n cube minus 20 200n minus 743 doesn't belong to ON square, because if you take the ratio of that with this and let n tend to infinity, the ratio goes to infinity. Therefore, this cannot belong to big O of n square. So, here are the examples which belong to ON square. Here are the examples that doesn't belong to O of n square. In this way, for any function, you can find out who belongs to O of n square by this test. Okay, question there? Ratio can be? Yeah. Yeah, even when it is oscillating, we cannot say one is the order of the other. Those two are not related by big O relation. If it is oscillating, then also it doesn't. Okay, we will give one example of that kind also, where when it oscillates, what kind of confusion it creates. Only when it converges and to a finite constant, that finite number could be any number. It could be 0 or non-zero, that doesn't matter. As long as it is finite, it is big O of f of n. If it doesn't converge, or if something confusing happens, then we cannot relate those two functions through big O notation. They are independent functions with different characteristics, that's it. One cannot be spoken in terms of big O of another. Not that between any two functions you can talk of one in terms of the other. Not necessary. The reason is, if you look at the graph of function, I will give two functions where f is not big O of g and g is not big O of f. In other words, both of them cannot be compared in whatsoever manner using this notation. I will tell you the importance of theta notation and big O notation, why we need. That also I will mention. Yes. No, it is not the limitation of this notation, it is the limitation of those two functions. They do not have they may have independently nice properties. In terms of order, they are not comparable. That's all. With respect to this concept, they are not comparable. This is not a limitation in any way. I will tell you the reason for big O. What big O tells you by the very definition here. This is an upper bound. Okay? So big O notation is to be used for upper bound. To show